Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand.
Yeah. Sand is silicon dioxide.
Yeah. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today.
The recent rise of electric vehicles has resulted in global demand for improved, high-consumption batteries. Recently, Elon Musk revealed that a new breakthrough silicon battery may be the answer. In today's video, let's take a closer look at this battery and what makes it so unique. Can this new technology change the EV industry? Silicon anode batteries are like an upgraded version of the common lithium-ion batteries. In the past, lithium-ion batteries used lithium as the main material, but now they use silicon ions instead of carbon or graphite. Elon Musk said that the new battery can store about 500 watts per kilogram more energy than the older ones. Not only that, it can charge very quickly in just 6 minutes and can provide a range of 600 miles or even more. But what is the price of this battery? The cost of making silicon anode batteries is expected to be less than $100 per kilowatt hour by 2025. In comparison, lithium batteries cost $134 per kilowatt hour. Using silicon anode batteries can greatly improve battery performance. For example, the Tesla Model Y in 2023 has a battery size of 75 kilowatt hours. If it used silicon anode batteries, the cost would only be $7,500, saving $2,550 compared to using lithium batteries, which cost $10,050 for the same vehicle. The price of a battery depends mostly on the materials used. Overall, the cost of producing silicon anode batteries is much lower than that of older types of batteries. The cost of materials has decreased rapidly in recent years, and this trend is expected to continue. In simple terms, silicon anode batteries are relatively inexpensive to make compared to other batteries. They are even cheaper than graphite batteries and have a similar cost to lithium-ion batteries. Furthermore, researchers have developed a method where they directly attach silicon nanowires to commercial graphite. This approach can reduce battery manufacturing costs by over 30%. It's a great solution for battery companies and consumers, helping them save money. But why is the silicon battery considered the highest capacity in the industry? Apart from lithium, silicon anode batteries have the highest capacity compared to other batteries. They can hold 9,786 milliampere hours of energy in 1 cubic centimeter, which is 3 times more than lithium, which can only hold 3,271 milliampere hours per cubic centimeter. In addition, silicon discharges at an average of 0.4 volts, which strikes a good balance between preventing the plating process and maintaining a reasonable voltage when not in use. This is much lower compared to lithium batteries, which have a general rating of 3.7 volts. Also, a silicon anode battery can last for 120 hours of usage, which is 15 times longer than a lithium-ion battery that only lasts for 8 hours. When it comes to real-world applications, silicon anode batteries have the highest overall capacity. Using silicon nanoparticles and silicon encapsulation are 2 effective methods to increase efficiency without any issues. But how is it possible for silicon anode batteries to hold such a high capacity? The most amazing thing about the silicon anode battery is how quickly it can charge. It has been shown that we can charge it up to 80% in less than 6 minutes. In comparison, the lithium-ion batteries used in Tesla Model 3s take up to 40 minutes to reach the same level of charge when using a 220-volt charger. That means using a Tesla Model 3 with a silicon anode battery pack would save you 34 minutes of charging time. Furthermore, Tesla discovered that making a small change to the battery can increase the vehicle's range by 20%. They demonstrated this in the Tesla Model Y, which saw its range increase from 316 to 379 miles. The same improvement was seen in the Model 3, with its range going from 250 to 300 miles, the Model X from 351 to 421 miles, and the Model S from 402 miles to 482 miles. All of this is made possible by the structure of the silicon nanowire anodes. The nanowire structure has straight and open pores, unlike graphite anodes. This allows the anodes and electrons to travel in a straight path, resulting in a very fast diffusion process and incredibly fast charging capabilities. As a result, consumer electronics using silicon anode batteries will last 30% longer per charge compared to normal batteries. But what about the energy density of the battery? Are there any other outstanding features? Scientists have made significant progress in battery technology by using silicon instead of graphite. This change could result in batteries with 20 to 40% more energy packed into them. In fact, silicon batteries have achieved the highest capacity when measured by weight with 4,200 milliampere hours. This is significantly higher than lithium, which has a capacity of only 3,828 milliampere hours. Furthermore, silicon anode batteries retain 80% of their capacity even after 500 cycles of charging and discharging. They allow for faster charging and discharging, thereby improving energy density. However, unlike carbon, silicon has the characteristic of expanding its lattice structure by as much as 400%. On the positive side, it only takes one silicon atom to store 4 lithium atoms, while graphite requires 6 carbon atoms to store 1 lithium atom. This means silicon has a 24 times atomic advantage over carbon in terms of storage capacity. To address the expansion issue, researchers have developed a method of forming silicon into porous nanowires arranged like a forest, with shorter wires in between. This structure allows the silicon to tolerate swelling and resist cracking, extending the lifespan of silicon anodes. But how do researchers use this technology to make further advancements? To achieve optimal performance in a silicon anode battery, researchers use an ionic liquid and a silicon anode. The silicon anode acts as a silicon ion, while the counter-electrode is a small disk of lithium metal foil. These two components are pressed together at a high pressure of 120 megapascals, creating a 2-electrode cell. The Pacific Northwest National Laboratory team has developed a scalable process to prepare porous silicon of micron size. This technique yields high amounts of porous silicon while maintaining a consistent temperature during the etching process. It also allows for the recovery and reuse of the etching agent. The team has also formulated localized high-concentration electrolytes specifically designed for silicon anodes. This formulation significantly reduces leakage, current, and extends the battery cycle life. The goal is to produce a silicon anode battery pack system with a capacity of 235 watt-hours per kilogram, equivalent to 15 years of calendar life and 500 discharge cycles. In terms of resources, silicon is abundant in the Earth's crust, so there is no scarcity issue. It is environmentally friendly compared to graphite, which needs to be mined and refined. China is the largest producer of silicon, followed by Russia, while the United States produces a smaller amount. In terms of safety, silicon anode batteries have several safety issues. They include a positive temperature coefficient, or PTC device, to protect against high current surges, a circuit interrupter to prevent excessive charging voltage, a safety vent to release gas during rapid pressure increase, and an external electronic protection circuit that opens a switch at 4.30 volts. Additionally, a fuse cuts off the current flow when the external temperature reaches 90 degrees Celsius. These features make silicon anode batteries a safer choice compared to graphite-based batteries. When it comes to Tesla's electric vehicles, silicon anode batteries can be applied as a promising alternative to lithium-ion batteries. They can store more ions and have a higher energy density compared to traditional graphite-based anodes. By using silicon-based batteries, Tesla could potentially enhance the performance and range of their EVs. However, it's worth noting that some lithium-ion battery manufacturers are already incorporating a small amount of silicon in their batteries. In contrast, GDI's approach uses 100% silicon, resulting in improved performance and reduced risk of lithium dendrite formation. Overall, silicon anode batteries offer exciting possibilities for various applications, including electric vehicles like those produced by Tesla. In fact, Tesla has confirmed that their cars currently contain a certain amount of silicon, but it's not enough to fully harness its benefits. Initially, Tesla's Model S had only 5% silicon mixed with graphite in their batteries. Most companies still use this 5 to 10% range. However, Tesla now incorporates a substantial amount of silicon, ranging from 10 to 50%, to enhance battery capacity and energy density. Extreme temperatures affect all cars, but electric vehicles like Tesla's are especially sensitive to heat or cold. Tesla's electric cars perform best when the battery temperature is around 20 degrees Celsius. Silicon anode batteries can tolerate higher temperatures, around 2.3 times more than lithium batteries. Lithium batteries have a safety range from 5 to 55 degrees Celsius, while silicon anodes demonstrate better performance due to faster reactions and ion movement at higher temperatures. If the temperature exceeds 80 degrees Celsius, the battery cell may suffer damage, and temperatures above 130 degrees can lead to melting and potential fires. In such cases, the battery's capacity deteriorates rapidly due to severe side reactions. While there are many clear benefits of the new technology, only time will tell if it is, indeed, the future of the EV industry. If you like this video, you may also be interested in this one, which talks about a new generation of robots unveiled by Elon Musk. Do you think silicon anode batteries are the future of power storage? Please share your thoughts in the comment section below.